Section 1. A cosmic slap. The birth of our moon. Our moon hangs in the night sky, a familiar, silent companion. But its origin story is anything but silent. It's likely a tale of cosmic violence on an epic scale. The leading theory for the moon's creation is the giant impact hypothesis. Picture this: about 4.5 billion years ago, when our Earth was just a baby, another planetary body, roughly the size of Mars, approached and then slammed into it. This impactor, we call it Theia, didn't just graze Earth. It delivered a cataclysmic, world-shattering blow. It would have been the single most significant event in Earth's geological history, a moment that reshaped our planet and gave us the moon. This isn't just a wild story. It's a robust scientific theory built to explain curious facts about the Earth-Moon system. Before the giant impact idea, other theories competed. Maybe Earth spun so fast it flung a blob of itself into space, or the moon was a wandering body our gravity captured. Those ideas had fatal flaws. The giant impact hypothesis elegantly solves many puzzles, matching the chaotic nature of the early solar system. Section 2. The case for a cataclysm. So what's the evidence? Why do so many astrophysicists find this story of a cosmic collision so compelling? Let's start with a simple, weighty fact: the moon's density. The moon is significantly less dense than Earth. Our planet has a hefty iron core, which gives it a high average density. The moon, however, is a lightweight. This suggests it lacks a large, dense iron core of its own. The giant impact model explains this beautifully. The collision would have primarily ejected material from Earth's rocky outer layer. The dense iron cores of both bodies merged and remained with Earth. The moon, therefore, was built from the lighter, iron-poor leftovers. Next, we look at the rocks themselves. When the Apollo astronauts brought back hundreds of kilograms of lunar samples, they gave us a direct window into the moon's past. These rocks told a fiery tale. They contain minerals that indicate they were once part of a vast, global magma ocean. The entire outer layer of the moon appears to have been molten at one time. A cataclysmic impact, releasing an unimaginable amount of energy, provides the perfect mechanism to generate this immense heat. The debris blasted into orbit would have been scorching hot. Section 3. Puzzles in the lunar story. But science is never that simple. A good theory is one that can be tested, and the giant impact hypothesis has faced some tough questions. It has some cracks in its otherwise elegant facade. The first major puzzle is a matter of chemistry, or more specifically, geochemistry. The theory posits that the moon formed from a mix of material from both Earth, Theia. Since Theia would have formed in a different part of the solar system, it should have had a distinct chemical fingerprint, particularly in its ratios of different isotopes. The problem? When we analyze moon rocks, their isotopic composition is astonishingly, almost suspiciously, similar to Earth's rocks. This isotopic similarity is a serious challenge. If the moon is a mixture of Earth and Theia, why does it look so much like it's made only of Earth? It's like baking a cake with flour and sugar, but finding it tastes only of flour. Some recent modifications to the theory try to solve this. Perhaps the impact was so energetic that it created a massive donut-shaped cloud of vaporized rock, a synestia, that thoroughly mixed all the material from both bodies before the moon condensed. Or maybe Theia just happened to form very close to Earth, giving it a nearly identical composition. But these are still debated fixes to a significant problem. Section 4. A cosmic verdict, for now. So where does this leave us? We have a leading theory: the giant impact hypothesis. It beautifully explains many fundamental features of the Earth-Moon system. Moon's low density and small core, Moon's once molten state, system's high angular momentum. It fits our understanding of a dynamic, violent early solar system. Supported by observations of distant star systems, it remains the best story we have. It checks the most boxes. No other theory has matched its explanatory power. It stands as the consensus among most planetary scientists today. However, we must face lingering questions with intellectual honesty. The isotopic conundrum, the moon looks like Earth's chemical twin, is a big challenge. It forced scientists to refine and complicate the original simpler model. No moon around our sister planet, Venus. Evidence for surprisingly early liquid water on Earth. These are loose threads that keep the case from being completely closed. These inconsistencies don't necessarily disprove the theory. They show our understanding is incomplete. They are the grit in the oyster, discrepancies that drive new research. The beauty of science is that it thrives on this tension. A constant dialogue between theory and evidence.
Which statement supports the giant impact theory for the moon's formation? What do moon rocks suggest about the moon's early surface? Which lunar feature supports the collision theory? What observation outside our solar system supports the theory? Why does the giant impact theory fit solar system formation ideas? Which evidence supports a link between Earth and Moon material? Which statement challenges the giant impact theory? Why is Venus mentioned as a problem for the theory? According to a criticism of the theory, moon rocks should resemble which body more? What actual rock evidence creates a difficulty for the giant impact theory?